आज हम लोग न्यूक्लियर फिजिक्स के कुछ क्वेश्चंस करने जा रहे हैं। तो लेट अस स्टार्ट। with the first question. First question is like this. You have lithium nucleus with kinetic energy 3.00 MV, and suppose it is sent towards a thorium nucleus. Then the question is, what is the least distance this lithium nucleus will achieve while coming to thorium nucleus, provided this thorium nucleus does not move. As you know, this lithium nucleus will have 3 protons and thorium nucleus will have 90 protons. And when lithium nucleus is coming towards this thorium nucleus, these protons will repel and there will be a repulsion force. So, what is the least distance it can attain? Suppose this least distance is D. Now this lithium nucleus is having kinetic energy, and while coming towards this thorium nucleus, it will convert into potential energy. What is the potential energy? Between two charges that you already know, 1 by 4 pi epsilon 0 Q1 Q2 upon R. In this case, if we equate kinetic energy to potential energy, we can write like this: 3 MeV is equal to this factor. We can write it as 8.99 into 10 raised to 9 volt meter upon coulomb, into Q1 is nothing but 3 protons, that is 3e. Q2 is nothing but 90 protons, that is 90e. And the distance we have assumed as D. By rearranging, we can find out D is equal to 8.99 into 10 raised to 9 into 3 into E is nothing but 1.6 into 10 raised to minus 19 into 90 E divided by 3 into 10 raised to 6. This mega has gone. Then into E cancels out, and this gives you 1.3 into 10 raised to minus 13 meter. This we can write as 130 femtometer, which is the unit for measurement of distances in case of atomic distances, because there are very less distances. So this is how this can be solved in just 2 steps. Now we can go to next question. Now the previous question is a little bit modified. Here we will take alpha particle, that is helium, and another nucleus is, that is aluminum. In this case, what we have to find out is, suppose we have to find out the energy. Find out the energy with which this helium nucleus is sent towards aluminum nucleus, so that it touches the aluminum nucleus like this. This is aluminum, this is helium. So in this case we have to find out the energy, means kinetic energy of helium nucleus. Here we see, suppose this is the radii and this is the radii of helium. So R1 is the radii of helium nucleus, and we can find out what is R1. R1 is nothing but R0 A power 1 by 3. Here R0 is a constant, and that is 1.2 into 10 raised to minus 15 meter. And A is nothing but the mass number of helium, and this we can write as 4, and this is raised to 1 by 3. So the R1 is nothing but 1.9 into minus 13 meter. Likewise, R2 is 1.2 into 10 raised to minus 15 meter into aluminum. What is the aluminum mass number? That is 27 raised to power 1 by 3. Oh, this will also come out as 3.6 into 10 raised to minus 15 meter. So, what is this distance basically? Suppose this is R, then R is nothing but R1 plus R2 is equal to 1.9 into 10 raised to minus 13 plus 3.6 into 10 raised to minus 15, and this will come out as into 10 raised to minus 15. Now we know this distance when they touch each other. So we can find out, suppose we send with some kinetic energy, and if they are touching, that means the potential energy here must be equal to kinetic energy, or you can say kinetic energy must be equal to 1 by 4 pi epsilon into Q1, Q2, and this R, and this is nothing but 1 by 4 pi epsilon, you already know, 8.99 into 10 raised to 9 Newton meter square plus Coulomb square into helium. Protons are there, that means 2e, into aluminum. Protons are there, that is 13e divided by 5.50 into 10 raised to minus 15. This will come out as, if you simplify this will come out as 6.79 MeV. So this is also a question of similar type with a little difference. Now we come to another question. Now let us go to the third question. Third question is like this. We have a alpha particle going towards aurum nucleus. Basically it is alpha nucleus with kinetic energy 5 MeV. In this case, when this is going towards this, then after the closest approach, this recoils in this direction, and this, suppose this is the closest approach, then this recoils in this direction. So we have to find out how much energy they will have while recoiling. We already know that as per our mechanics, V alpha final is nothing but M alpha minus MAU divided by M alpha plus MAU V alpha I. And V or final is nothing but 2M alpha divided by M alpha plus MAU V alpha I. So this we have to remember for solving this question. Here this aurum nucleus is recoiling in this direction, this is recoiling in this direction. Then we can write as what is the kinetic energy of final kinetic energy of aurum is nothing but half MAU into VAU square. No problem. Now this we can write it as half MAU 2M alpha upon M alpha plus MAU V alpha I square. This can be again simplified as K alpha I as 4 MAU M alpha divided by M alpha plus MAU whole square. Here we can put our values. What is the M alpha I is nothing but MEV, and then 4 into MAU is nothing but 4 U into 197. U is nothing but atomic unit, mass unit, divided by 4 U plus 197 U whole square. And this will give you, when you will solve this, because U will cut down here, the units will not matter, then this will be nothing but 39.39 MeV. Likewise, you can find out MK alpha F, which is nothing but 1 by M alpha V V alpha F square. V alpha F square we know. If we put down this and likewise we can find out, then it is nothing but 4.6 MeV. So this is the kinetic energy of the recoiling nucleuses. If we now here we can see that K A U final plus K alpha final is nothing but 0.39 plus 4.61, and this is nothing but 5 and this is nothing but the initial K alpha. So our this principle of conservation of energy is satisfied. Now we can go to the next question. Next question is like this. We have a penny whose weight is, or you can say mass is 3 gram, and it is the material is what? Copper. Now we have to calculate the energy required to separate all the neutrons and protons of this nucleus. So we have a 3 gram penny with nucleus करना चाहिए. This is a copper 63. Then now we have to find out the energy. What will be the energy required to separate the neutron, or you can say all the nucleons from the nucleus. What is given is mass of copper is nothing but 62.92960 AMU. Then mass of neutron is nothing but 1.0866 U, and mass of proton plus electron is nothing but 1.00783 U. Now, what is basically the nuclear binding energy? Nuclear binding energy is nothing but the energy required to separate all the nucleons. Okay? Here in this copper nucleus there will be 29 protons and 34 neutrons. This we have to remember. So we know delta E is nothing but delta m c square. So delta m is nothing but delta E. Now we can write as what is the mass of 29 protons. Here it is given protons plus electron, that is 1.00783 U, and what is the mass of 34 neutrons into 1.00866 U. This is the mass on the right hand side. Now minus the left hand side, what is there? That is 62.92960 U. That is the mass of the copper into, that is C square is nothing but 931.5 divided by UMEV, because C square is nothing but, if you remember, 939 MeV divided by, so here you can calculate this. This will come as 551.4 MeV. Now this energy is required for one nucleus. Here you can see I have written the mass of P plus E. In this actually electron's mass is also included, but this will cancels out from here because in this also electron's mass is included. So this electron's mass cancels out. So you get purely the difference between proton and neutron's masses. That now, but the penny's weight is 3 gram mass. So what is the total energy? Is nothing but 3 gram divided by 62.92960 gram per mole, because we know for 1 mole the copper's weight is 62.9. So how many moles will be there? This will be this. And how many moles will be there in 3 gram? Like this. Into, we know per mole how many atoms are there. That is our Avogadro's number. That is 6.202 into 10 raised to 23 atoms per mole. So that means for one nucleus, this energy is there. If we multiply this many atoms into this energy, then we can find out the total energy. That means total energy equal to, again, into 551.4 MeV. So it will come out as 2.91 into 10 raised to 22 atoms into 551.4 MeV, and this will be equal to 1.6 into 10 raised to 25 MeV. So this is the final answer. Now we can go to next question. Next question is also a little bit similar like this. You have a alpha particle or alpha nucleus, alpha particle, that is, now you have to find out the energy required to, one, remove a proton, remove a neutron, and remove remaining proton and neutron. You have to find out the energy in step by step manner. So let us write first the equations. You have alpha particle Now suppose one proton is removed. For this, the equation will be, this will be equal to, okay, then from this now you have to remove one neutron, then neutron plus 2H, and from this what is remaining is proton plus neutron. Now here what is given is 4He, mass is 4.0260 U, then 2H mass is 2.01410 U, then 3H mass is 3.01605, then 1H mass is 1.0783 U, and mass of neutron is 1.0867. So now find out A. A is 4He, but this A is nothing but 4He P plus 3H. We can write out this as 4He. It's nothing but, this is 1 plus 3H. So what is delta E? Delta E is nothing but M1H plus M3H minus M4He into C square. If you write as 931.5 MeV upon U, you will get as 19.8 MeV. Here this M1H mass is there, M3H, M4H. Likewise, can find out the, like this in the case of B, if we see this equation, and apply this equation, then delta E is nothing but M2H plus Mn minus M3H into C square, and this will give you as 6.26 MeV. And if you go for C, then we can write as 2H. This equation we can write as 1 plus N. So delta E is nothing but M1H plus Mn minus M2H c square, and this will give you 2.23 MBE. So now with this process you can see that all the nucleons have been taken out. So total energy here, from here we can find out total binding energy is nothing but 19.8 plus 6.26 plus 2.23 is equal to 28.3 MeV, or sometimes it is also called what is the total binding per nucleon. So BE per nucleon is nothing but 28.3 upon A, that is 28.3 upon 4, because 4 is the mass number. So this is how you can find out total binding energy together, or you can, if you want to, find out the energy required to separate the single protons, neutrons, or single proton, like this. Okay, I hope you understood these problems. Okay.
If you like this video, please do share and do subscribe. Thank you very much.